let me just introduce our speaker this morning. So Maryam, it's my pleasure to introduce Maryam. We first met in graduate student at Berkeley, actually. It's been a while since then, and since obtaining her PhD from Berkeley, Maryam has gone on to an amazing academic career, which is including being an assistant professor at ETH. And now she's an assistant professor at our Canadian neighbor, UBC, in electrical and computer engineering. Maryam's list of awards includes the NASA High Potential Individual Award and NASA Excellence in Publication Award for her work on air traffic control systems in conjunction with NASA Ames, and the European Union Starting Grant for her work on multi-agent decision-making and control and power systems. So one of the things I admire the most about Maryam's research is that it spans both theory and practice. So for example, she's made fundamental theoretical contributions to learning and games, while also developing control and decision-making algorithms for real-world systems, as is evidenced by the aforementioned recognition by NASA. So in general, Maryam's research focuses on multi-agent decision-making in uncertain and dynamic environments, where she seeks to design algorithms for optimization and learning, drawing on tools from a variety of domains, including game theory, control, and machine learning. So she's a perfect fit for our seminar series this quarter. And so today we'll hear about some of her recent work on learning in multi-agent systems. So I'll just turn it over to you now.
Okay. Hello, everyone. Thank you, Lillian, for the kind introduction. It's a pleasure to be here with you. I wish I could be there in person, but yeah, so hopefully in near future, once the borders open up again. Okay, so it's a pleasure to share some of my recent work with you, and today I'll focus on learning in multi-agent systems. So my broad research area is control theory, which is decision-making in environments that are dynamic, in other words, they're changing and are uncertain. And just a little bit of background, what we see in a control system is they have been evolving from single systems in fairly predictable environment to multi-agent systems, for example, single power generator control to an intelligent smart grid where we have a number of prosumers and consumers connecting and introducing uncertainty by their renewables production and balancing supply and demand of electricity. And we see from single vehicle control to an intelligent transportation network where we have to coordinate number of decision makers, and also from robots working in fairly predictable environments to robots that help humans in dangerous and complex tasks. So my research agenda is basically managing these increased uncertainties in the autonomous system. And there are two classes that I focus on. One of them is how can we guarantee safety of the autonomous system and how can we coordinate the interactions. And so my work focuses on safe learning and control, and a large aspect of my past work and current work is stochastic reachability and formal methods, safe black box optimization, and applications in transportation and robotics. And then on multi-agent, on the second aspect, multi-agent learning and control, I focus on learning of equilibria, no-regret learning mechanism design, learning distributed controllers, and applications in transportation energy system. So for the rest of this talk, I will focus on this second topic, multi-agent learning and control, and mainly on the first two bullet points, black box learning of equilibria and gray box no regret learning. Okay, let me see, there's a chat. Okay, great. Okay, what are multi-agent systems? They're interacting agents which are coupled through their objective and constraints. For example, in a smart grid, each producer or consumer wants to minimize its electricity bill, but the price of electricity depends on production and consumption of all other players. Similarly, in an auction, players want to get the maximum reward, but whether they get the item or not depends on the decisions, on the bids of the other players and the constraints of the central decision maker. Similarly, in multi-agent robotics or in a transportation network, where here the travel times of the vehicle depend on the congestion of the roads, which is a function of everybody else's decision. So the question we like to focus on is, how do agents learn to optimize given only local information and no understanding of the decisions of the other players, or in particular also their cost function, because that may depend in non-trivial way on the decision of other players. So I'll talk about black box learning in games as regret minimization, and learning in games using priors to address this question. So let's just formulate the multi-agent learning problem. We have n agents or players, and they each choose an action, let's say AI, and the joint action is boldface A, which is the decision of player I, and the decision of every other player, a negative I. And then the agent I experiences a cost JI, which is a function of her decision and others' decision. For example, price of electricity depends, that the producer or consumer experiences depends not only on her production, but also, or consumption, but also the total production or demand of electricity. Okay, so this is an example of a multi-agent game. You see that the objective functions of each agent are coupled with the others through their decision. And so we know that optimal local decisions here are characterized by Nash equilibria. So a Nash equilibrium is a joint action where no agent has incentive to unilaterally deviate from her choice. So given fixed action of the other players, agent I is minimizing her cost. Okay, and it's easy to visualize this in a two-player zero-sum game where one player is minimizing a cost and the other one is maximizing, and this Nash equilibrium is a saddle point. Okay, so this is the notion of optimal local decision that we are looking for. It is stable in the sense that no agent has incentive to unilaterally deviate from her choice. So what is the problem of seeking equilibria with black box information? So each player does not have an idea of what her cost function is, for example, price of electricity, because she might not know the price function. She can just play an action and get her reward for that chosen action. So this is like a black box model. So we can ask the question of how could the agents learn in this setting, and this is kind of like a standard black box optimization, and we can think that, okay, agents can try to estimate the gradient of this JI. The challenge in a game setting is that, so if agent I queries the function at AIT at some time t, and then at AIT plus delta, and try to use finite difference, she cannot do that to estimate her gradient because other players' action might have changed at that time. So if her cost decreases, it's not clear if it was because of her delta or if it's because the others change in their decision. Okay, so it's a little bit different because of this game and coupled objectives. It's a little bit different than the black box optimization. Okay. Good. So I'll just talk about the approach to do the learning in games, and I give kind of different ways to a couple of different interpretation of this. So the idea for learning is that each player needs to randomize her actions. So she chooses action AI, which has it's distributed according to a distribution whose mean is mu I, and this mu I is updated greedily based on observed cost. And then there is a variance sigma I, which encourages basically exploration of non-greedy actions. And kind of one interpretation is, if you think of decision, it's a decision making when you are faced with unknown costs, such as multi-arm bandit, and you don't know the reward of each of these arms. You have to introduce, rather than just sticking with the arm that has given you highest rewards, you want to explore the other arms. So you have to introduce some randomization. But the more technical reason for doing this is that if you now look at the very simple algorithm where agent I is choosing AIT, it's mu I plus some random term, and she gets the reward JIT evaluated at this action, and then updates her mu I, the state of her decision, according to something that looks like a gradient descent. So mu I t plus 1 equals mu I t minus a step size or learning rate times the experience cost plus this randomization. Okay, so this is the algorithm. Then you can show that this JIT WIT is a sample of the gradient of agent I's cost function, a smooth version of the cost function. So what is meant by that is, in expectation, this second term is equal to the gradient with respect to mu I of the smooth, so the integral of ji with respect to the probability distribution that you're choosing. Okay, so by doing this randomization, agent I can get a 1-point estimate of the gradient of her cost function. Okay? And this approach is also quite known in when you're doing a bandit optimization problem, which I will talk about the connection with this. So just to remind you, agent I could not use finite differencing, for example, to learn the gradient, because the action of other players might have changed as she changes her action. And so she really needed to have a way to do a 1-point estimate of the gradient. And by introducing this randomization, we can get a 1-point estimate of a gradient of a smooth version of the cost function. Okay, I'll just pause and see if there are any questions so far. So the whole algorithm is basically this, quite simple. So let's just look at the result then of convergence to Nash. So we need some assumptions for that. So let's say that the agents are playing a convex game. So each JI is convex in AI given fixed action of other players, A negative I, and the game pseudo gradient MA, which is stacked version of gradient of each player's cost function with respect to her decision variable, is Lipschitz and is strictly monotone. Okay. So under these two assumptions, we can show that if we choose the step sizes or learning rates, in other words, and the variance of this exploration such that they satisfy some summability condition, then the state of the algorithm converges almost surely to a Nash equilibrium. Okay. So to summarize, we had a multi-agent setting problem where each agent did not know the cost function ji, but could get black box information about ji, and we can this under certain assumptions, this algorithm converges to a Nash equilibrium. Oh, let me see, there's a chat. Okay, by convex game, I mean that this JI is convex in player I's decision variable. I can also introduce constraints. For simplicity, I remove all the constraints on action of player. So AI can be in some convex compact set. Okay, so that's all I mean by that. And now I'll briefly discuss the proof, and I think you get more intuition why we need this convex game assumption. So there are a couple of steps to the proof. The first one is that, okay, so we define the Nash equilibrium. So each agent is choosing the optimal action given the strategies of other players fix. So first of all, we know that Nash equilibria exist in convex games. So in non-convex games, this is not necessarily true. So at least we know we're looking for something that exists. And furthermore, we know how to exactly characterize them. So in convex game, so this game pseudo gradient, which is a stacked version of gradient of each player I with respect to her decision variable. So the A star is a Nash equilibrium if and only if a star satisfies what's called a variational inequality problem given this pseudo gradient map M, and this is the action space of the players. Okay, so A star transpose A minus A star greater than or equal to 0 for all feasible actions. Okay, so if this MA was had a symmetric gradient, then this would be a potential game, and this would map to a optimality condition for a single function. Okay, but in general, this MA might not have a symmetric gradient, and so the games are more general than optimization problems, but they can still, their Nash equilibria in convex game can still be characterized exactly the same way that the solution to an optimization problem would be characterized, where this MA in case of optimization would be just the gradient of the function. Okay, let me see if there are any questions. Just pause. Okay, so this is one thing about Nash equilibria and convex games. So we know they exist and we know how to characterize them. The second result that the proof relies on is just about convergence of random variables. So we have basically some random variables, ZT, beta T, zeta T, GT, and if in expectation they satisfy certain decay condition, then you can show that this limit of zeta exists and is finite. And furthermore, this second term is summable under the condition that this beta random variable is summable and zeta T is summable. Okay, this is a standard result in just a sequence of random variables. So let's just see how we will use them. So basically we let these random variables, so we can think of this very similar to kind of a dynamical system theory proof, where this mu minus mu star, so iterates of the algorithm minus the Nash equilibria, you look at the norm of this. And so the algorithm, you can write it equivalently as mu t plus 1 equals mu t minus the step size times what is a pseudo gradient plus a bias and a noise term. Okay, and then you can, just doing some algebra, you can show that in expectation, this random variable conditioned on the past information is decreasing. So it's less than or equal to mu t minus mu star squared plus some GT, and by choice of the step size and variances, you ensure that this term is summable. And then just using the previous result, we can conclude that this second term is also summable. And then using the fact that the Nash equilibria satisfy the variational inequality, then you can show that if this is summable, then mu t minus mu star has to converge to 0. Okay, so this is a high level idea, but the basic idea is to write the iterate of the algorithm like a stochastic approximation algorithm, and then you have a kind of the gradient function, and then you have a bias and a zero mean noise term, and appropriately bounding these terms using the step size and variances, and then this is the optimality condition for Nash equilibria. Okay. Good. I'll just give a very simple example. So here's the electricity market example I mentioned at the beginning. So here we have a number of producers, and they're deciding their production amount over n periods. And then they also have they have a local production constraint, how much was the maximum and minimum they can produce. This AI, some convex set. And there's also a network capacity constraint on the total production. And then players' eyes cost function has a term that depends on her own decision. And then there is a term that depends on the price of electricity. So it depends on everybody else's decision. And this is unknown to the players, okay? Because the price of electricity is unknown. So we want to see how they can learn Nash equilibria just by playing an AI and observing the price of the electricity. And this satisfies the conditions discussed for the convex game, and we can basically plot the iterates of the algorithm. So here you're seeing the distance between the iterates of the algorithm and the Nash equilibrium as the algorithm progresses. And the colors correspond to increasing number of players. So what we observe is usually we have a fast initial decrease at the beginning and then very, very slow decrease towards the optimal solution. And especially this gets smaller with the larger number of players. So we still don't know what's the optimal convergence rate in terms of learning in games. And this is something that I am basically exploring right now. So what is the best rate that the agents can converge to the Nash equilibria? How does that rate depend on the number of players and how we can speed it up? Oh, okay, there's a question. Yes, in the example that I showed, in the example I discussed, there's always a Nash, and in general in the convex games, there's always a Nash. And if the game pseudo gradient is also strictly monotone, then there's always a unique Nash equilibrium. Okay, other questions? Okay, if not, I want to just make some connections with learning in games also as regret minimization. This is something that I alluded to in the first part. So let's talk about kind of bandit learning and see the connection with learning Nash equilibria. So in a bandit learning problem, basically each the algorithm or the agent plays an action, and then she receives a cost function for that action. Okay, and that cost function is changing over time. Okay, so and then regret is at time capital T is the sum of the experience cost minus the sum of costs evaluated at the best action in hindsight. Okay, so regret is what we try to optimize in a bandit learning problem, the lack of better benchmarks, basically. And so we call an algorithm no regret if is R of T grows sublinearly in T. And we know no regret algorithms exist. They're a topic of research for the past couple of decades extensively. Now we can think of our game as a bandit learning problem, because as I mentioned, while agent I can choose her action, AIT, she has no influence over the action of the other players. So even though this JI is a constant function from the perspective of player I, JI is changing with respect to time, because at each time, even if she keeps her action constant, she's gonna get a different cost function since other players will change their action. Okay, so we can think of a learning, black box learning in game as a bandit learning problem. Okay. So what do we know about no regret learning and equilibria? This problem is very well studied in finite action games. And in particular, we know that if each player adopts a no regret algorithm, the time average sequence of action of player converges to what's called a coarse correlated equilibrium. So it's a very coarse notion of equilibrium. It includes Nash equilibrium, but in general, it's not a very strong notion because it can include actions that have probability on non-rational basically actions. But okay, the point is we know connections between no regret learning and equilibria in finite action games. And this hasn't been as explored in the infinite or continuous action games that we focused on so far. But we can, what we showed that is our algorithm, and this is the, basically it's just this, it's a very simple algorithm, is a no regret algorithm. And actually the last action, the last iterate also is converging to the Nash equilibrium. So we are showing a much stronger result because we're showing convergence to Nash, which is a strict subset of course correlated equilibria, and not for the time average sequence of play, but rather for the final action of the players. But of course, we are relying on the fact that this is a convex game. So we are using the convexity structure to show this result. Okay, so to summarize, in a for a black box learning equilibria in a convex game, we can have a algorithm that converges, that is no regret, and also converges to a Nash equilibrium. Okay, let me see any questions. Okay, so as I mentioned, this is under assumptions, convexity, also strict monotonicity of this pseudo gradient mapping. And what I want to focus a little bit on is this strict monotonicity of the pseudo gradient, and to understand how strict is this assumption. Okay, so actually, it is a quite a strict assumption, because there are a large class of games whose game mapping, the pseudo gradient mapping, is not strictly monotone. For example, zero-sum games. This is a simple zero-sum game, matching pennies, where two players reveal a penny at the same time, and if it's a head player, row player is getting a 1. A cost of 1, and the column player is minus 1, and if they don't match, then the row player gets a -1 and column player gets a +1. And for this very simple game, the game pseudo gradient is not strictly monotone. It's actually identically equal to 0, and all the algorithm does not converge, because as I so here is, you just show the if you evaluate, if you implement our algorithm, you can show that basically you're not converging to the Nash equilibrium. And the Nash equilibrium actually is to choose head and tail with probability 1/2, but we are not converging. But actually a large class of what was shown in the past few years is that a large class of no regret learning algorithm also do not converge. So this is not just a limitation of our algorithm. So in particular, all these follow the regularized later algorithm, which are no regret, also diverge. And there is an interpretation of this that you can, if you, as I mentioned, if you think of game pseudo gradient, look at this Jacobian, then there is the symmetric part. And if this game was potential, you would only have this symmetric part. And if the game is not potential, you also have an asymmetric part. And this asymmetric part is causing basically this non-convergence issues. And if in this particular example of matching penny, this nabla M is completely asymmetric. Okay, and there's a connection between there's been a lot of kind of research on this to try to interpret it like a Hamiltonian system where some energy is preserved, and how to kind of get away from this issue of oscillations when you don't when you have the asymmetric part in the game, for example in the zero-sum games. Okay. So in summary, if we don't have a strict monotonicity, no regret learning algorithms do not in general converge to the Nash equilibrium. And so what can we do? And there's been a lot of work again over the past couple of years, especially because this non-strict monotonicity arises, as I said, in a large class of games, including zero-sum games. For example, in min-max formulation, which arise in robust optimization, robust control training, generative adversarial networks. And then we can ask the question, actually, this is, if you look at the variational inequality formulation of this, basically these VIs are monotone, but not strictly monotone. And we know that there are algorithms for monotone VIs, such as extra gradient algorithms or optimistic mirror descent, and you can show that these algorithms converge. But what we wanted to look at is this black box learning, and these algorithms are not readily applicable to black box learning because we don't assume we have any gradients, and so we don't have extra gradients either, and we cannot implement implicit algorithms that players can only play an action and observe their cost. So it's like a zero order information setting, and the extension of these algorithms to zero order information setting is non-trivial. What is the connection between the strict monotonicity and the so if so basically in this non-strictly monotone example, this MA was anti-symmetric. So if this MA is anti-symmetric, you cannot have a strictly monotone because this inner product should be strictly greater than 0 for the game map to be strictly monotone. That answers the question. Okay, so I want to now briefly talk about how to do a zero order algorithm to learn Nash equilibria in this setting when we don't have strictly monotone. So we have monotonicity, so we do assume we have monotonicity, so this is greater than or equal to 0, but not strictly. And basically we introduce a regularization to our algorithm. So this was the original algorithm, mu I. The state of player I is updated based on her past state, the step size, and the experienced cost scaled by this random number. And then we add a regularization, which the epsilon t, which is time varying. Okay, so this can still be done under zero order information. We don't need to know the gradients. And so this is as if each player is minimizing a regularized version of her cost function. Okay, and so then we can show that if this game map is pseudo gradient is only monotone and Lipschitz, we can find a set of variables eta, sigma, epsilon, such that these are the original conditions for convergence that we had. And then this is a condition, these conditions are about the growth of this regularization term with respect to the step size that need to be satisfied, so that we can still prove that we converge almost surely to a Nash equilibrium. Okay, so by introducing this regularization and controlling the epsilon t appropriately with respect to the step size, then we can show that we can still have a zero order black box learning algorithm that converges to a Nash equilibrium. And in particular, so often the way we choose this should be eta, sorry, I changed the variable. The way we choose these variables is just by choosing P series and then controlling these coefficients of T so that they satisfy these conditions. Okay, and then in this learning and matching penny, we can, for example, and other zero-sum games, we can show that the algorithm converges to a Nash equilibrium. Okay. So the proof is similar to the previous proof, but we just need to carefully account for this time varying regularization term. I won't go into detail now because there is one more aspect of learning in games that I want to talk about, as is sort of a little bit of a different view of how to do learning in games, and I'd like to share that with you. Let's see, any questions? Oops. Okay, so here, so far, I talked about convex games where we know that Nash equilibrium exists, and then we can basically use convex optimization tools with some modifications to look at learning in games. Okay, and now I want to go like beyond convex games and look at, for example, non-convex games such as finite action games, and see what we can do with this. And this work actually comes from collaborating with computers. One of the my colleagues who's in computer science, and so it has a little bit of a more CS flavor, where we said that, okay, in this case, we're going to assume some Bayesian prior agent's cost function. So still we are in a learning in game setting where where each agent does not know her cost functions, but let's assume some prior. In particular, suppose that agent I's cost function is a sample of what's called a Gaussian process. So basically, it's a random function. It has a mean GP. It has a mean and a covariance, which is also called a kernel. And so if you look at, for example, these three different plots could be samples of a Gaussian process with mean 0 and certain covariance function. And this covariance needs to satisfy certain conditions. There are different examples of kernel functions that satisfy as a covariance, then they encode similarity between nearby points. So then the question is, the agent is basically trying to learn her cost function under this prior assumption and the observations she makes. Okay. So the agent, so learning in the GP. So this problem, by the way, is well studied in a single player case, and we are just giving it a multiplayer flavor and see what we can do there. So agent I, as before, observes her cost for a played action AL, so L from 1 to T. And then she can formulate the stacked version of this cost and the covariances, and she can then update the mean function of this Gaussian process and its variance based on the past obtained data. This is just Gaussian process regression. So if you have jointly Gaussian random variables and you observe some of them, how do you update basically the mean and variance of the Gaussian? So this is exactly what it's doing. It's using its past observed cost and the evaluation of the covariance matrix at past observed actions to update the mean of the function and the variance. So what happens is here, if you make these observations at these points that are in with plus, then so here this gray band is the uncertainty band you have about your function at the beginning without any data. And after making some observations, you know the value of the function very well at the points that you observed, whereas the uncertainty is still large in between the observation points. So you updated the mean and the covariance of this function. Okay, but the point is you can do you can use this prior to update your cost function model, its mean, which is captured by its mean and covariance. Okay, so what do we do then in terms of the learning agents? So as I mentioned, now we don't necessarily have a Nash equilibrium in this non-convex setting. So we're not going to look necessarily for a Nash equilibrium, but we're going to assume that players are trying to minimize the regret. Each player is trying to minimize the regret because, as we saw, we can think of games as a bandit learning optimization problem. So player I's goal is to minimize the regret, which is the her experienced cost minus the cost evaluated at the best action in hindsight. Okay, and so in this case, we are looking at a banded learning in a game because we said that we can think of Ji as a time varying function since agent I is not aware of actions of the other players. And so we want to use this GP Gaussian process models to think of how can the agents minimize their regret. And now here again, we make a connection with existing no regret algorithms, in particular the multiplicative weight object algorithm, which is a standard no regret algorithm. It works under the assumption of finite action games. So if each agent's action set is, let's say, n actions, and it initializes the weight of each actions according to some to uniform distribution, and eta is the learning rate as before. And it samples the actions according to this distribution, observes the cost, and updates the weights based on this observed cost. Okay, and we know that this multiplicative weight algorithm achieves the optimal regret rate. The issue is that it requires full feedback, so it requires agent to observe her cost for all her actions, not only for the played action. Okay. So what we have available in this learning in game is that we have partial feedback. Each player can observe her cost for the played action. And additionally here, I call it gray box because we assume that she can observe the other player's action or an aggregate version of them, but she cannot evaluate JI at different points. Okay, she can just see JI for these played actions, and she might be able to see also AT negative I. Okay, so then the idea of this is to use the GP model to learn to mimic the full feedback information. Okay. Okay. So how do we mimic the full feedback information? So this is the mean function of the Gaussian process that we are learning and updating based on the data. And we can show that we can come up with an optimistic estimate of the loss function of each agent by appropriately choosing the beta t, and sigma was the covariance or kernel function of the agents. So if you choose this beta t according to this formula where gamma t is what's called the maximum information again, then you can show that with high probability this LT is a lower bound on the actual loss function. So you get an optimistic estimate of the loss function of the agents. Okay, so by using this, basically we use this as, instead of JI, we use the lower confidence bound on JI, which is something we can calculate using GP prior, even though we don't know JI, because we don't know the functional form of player I's cost function, we can estimate a lower confidence bound on it. And so basically we plug in multiplicative weight of that algorithm, this lower confidence bound. So this is exactly the multiplicative weight update algorithm, whereas the agents are estimating their cost optimistically, and they are repeating exactly what they were doing because they didn't know JI, but they could construct an optimistic estimate of it using their experienced cost function. And then we can show that by appropriately choosing this delta and the reigning rate, we can have a no regret algorithm in this setting. Okay, so this what n was the number of actions, t was the horizon, and this gamma t is dependent on the kernel that's chosen for the GP model. And it's called the maximum information gain, but the point is for most kernels, it grows sublinearly with respect to square root of t. Okay, so this whole term will be sublinear in t. And I just want to briefly talk about the proof. Oh, well, first, let's summarize. So there are different ways, there are different banded learning algorithms. So in the hedge algorithm, which the multiplicative weight update is an example. So we have full feedback information, and this is a regret rate. In the XP3 algorithm, we have banded feedback information. So we only observe JI of T of AT, and then we have a dependence on the number of actions that can be large. Oops. And in the proposed algorithm that we have, where we try to learn these functions based on partial feedback, we have a much better dependence on the number of actions than the Bandit algorithm, because this dependence on root n has disappeared. But we have an additional term that arises because of this approximation of the functions with the GP. Okay. So the summary is that these games are special class of Bandit learning problems. So we can exploit their structure, in particular that this JIT is not completely, it's not really a time varying function. It's only time varying because the dependence on action of the others. So we can, if we can try to estimate that and learn these functions, we can improve the regret, right? Okay. Good. I'll just briefly talk about the proof because it's not very hard. So this is a regret of the algorithm. So the experience cost for player I minus the cost evaluated at the best action in hindsight. And just because we know how to build high probability lower bound on this JI, we can bound the regret using these lower confidence bounds, exactly like this. So there are two terms, LT, AT, the experience, some lower confidence bounds at the cost, and the lower confidence bound evaluated at the best action in hindsight, plus some term that's coming from the fact that these are just the probabilistic lower bound on the algorithm. And then the first term, using multiplicative weight algorithm under full feedback, we can bound this. And then the second term, we can bound this due to the choice of beta t that we are making. So then putting these together, we get the bound that's shown here. Okay, I'll just end with one case study. So here's an example in a transportation network. It's a well-studied problem where drivers are trying to minimize their travel time, but they don't know congestion model of the road or choice of other players. So as a feedback, they choose some routes and they observe their experience travel cost. And this is a finite action game where each player is choosing from a number of finitely many routes. And then we use this GP approach to minimizing regret and look at the performance of this algorithm. So here we implemented it on a standard transportation testbed, which is called Zeux Faults, and it has 24 nodes, I believe, and 76 two-sided edges. And so they are using this GP multiplicative weight algorithm for their regret minimization. And here is the congestion of the network if they're doing shortest path, which of course is not very intelligent because it's not accounting for other players' choice, and this is a congested links. And then this is the congestion of the network after running this algorithm for 100 iterations. Okay, so more details also are in the paper in terms of comparison with other no-regret learning algorithms, such as Hedge and XP Twig. Okay, I think now I just summarize what we talked about. So we talked about learning in games. First, we talked about convex games and algorithms to learn Nash equilibria under the assumption that players don't know their cost functions or their gradients. They have as a feedback only the experienced cost. And the idea in this algorithm, which is like a stochastic gradient descent, that basically you kind of go in the approximate in the direction of the gradient, where you do a 1-point estimate of the gradient, and you introduce some noise in your next query point in order to be able to do a 1-point estimation of the gradient. Okay. Then we looked at non-convex game, and we looked at algorithms to learn correlated equilibria, or in other words, no regret algorithms. And we talked about how to bring GP Gaussian process Bayesian prior models to learn the cost functions. Rather than learning optimal actions, we first learn the cost functions and then use that to implement a no regret algorithm. And we saw that we can have vanishing regret for each learning agent with better dependence on number of actions than a complete black box case by learning these cost functions. Okay, so this is also again coming back to my overall research topic, which is kind of control system. As I mentioned, I look at two topics: system safety. So how can we ensure safety of learning-based controllers, and also subsystem coordination, such as learning equilibria and mechanism design. And so in this talk, I focus on this latter aspect, some subset of this latter aspect, and there are many kind of open questions at the moment that I'm exploring, such as optimal learning rates and including heterogeneity in the learning dynamics of of different agents, and also looking not just at the static games, but at dynamic games. So I just like to thank my collaborators that the last part of the talk on Bayesian learning was with my PhD student, Pierre Giuseppe, and then my collaborator, Andreas Krause, in the CS department, and his student. And then the first part of the talk on convex learning was with my colleague, Tatiana Tatarenko, who is at TU Darmstadt. And here are some relevant references, and I'm happy to answer your questions. Thank you for your attention.
Thanks, Maria, for a great talk. So yeah, I'd like to open it up for questions if people have any. You can just unmute yourself. It's a little hard to hear you, Tanner.
Is this better?
Yeah.
Yes.
Okay. In the part where you're talking about the convex games when you do not have the monotonicity, and then you showed that it's like cycling. So there, does the time average converge to Nash?
Yes, in the zero-sum game, you can show that the time average converges to Nash, the finite action. Yes.
Okay. Or in the
Yeah.
okay. So you would have like also with this zero order method, maybe the continuous time version of it would be recurrent, or
yeah, actually they analyze the continuous time version of it to show that you have these cycles. This paper
yeah, so that would also, I guess maybe not exactly sure what the continuous time version would be with zero order feedback with that.
So these papers, I think Mertikopoulos 2018, they actually look at the continuous time version of these, all these no regret algorithms, and they show that in this, like just the matching pen in the zero sum games, and in particular in games where you have Nash equilibria in the interior of the feasible set, you have this recurrent, basically cycles. Yeah, it's called cycles in adversarial learning, and exactly they show that.
So I'm wondering, like, would that be able to be shown with the zero order feedback like you're using?
Yeah, I think it would be. So they assume they have the gradient information, I believe, there, but basically we are estimating the gradient. So you're asking if we can show the same kind of cycles if we are doing. I would think so, but okay. Yeah. They did the analysis with the full gradient information. It's a good question. With the stochastic case, what we show what kind of equivalent statement we can say. Yeah.
I suspect that you can show it because, I mean, essentially you're just reducing everything to the stochastic approximation kind of update, where those tools for like ODs have been used before.
Right.
Just might have these variance and bias stuff that you need to control for. So
you need to kind of account for them, but I mean, in simulation, we do see these oscillations, but exactly what precisely we can say about them, I don't know. Yeah.
Any other questions? Oh, go ahead, Maryam.
Hi, yeah, I have a quick question actually on this same slide. Yeah, so is this decomposition representing somehow decomposing the game as a potential part and then something else?
Exactly. So because if the potential, so for the if we don't have a asymmetric part, then the game is potential, because it's basically there exists a function whose gradient would be the pseudo gradient of the game. And so actually the optimization techniques carry kind of very easily to this class of games, because it's as if the players are minimizing some same function, which maybe we don't know what it is, but yeah, but in terms of analysis. But in general, the game is more general, because we don't have just a symmetric part, but we also have the asymmetric part. And then the analysis becomes a little harder. Yeah, but exactly.
And the asymmetric part is always going to be oscillatory, or can it be something else as well? So is it anti-symmetric or asymmetric is more general?
Anti-symmetric. What do you mean? Sorry, is it?
So H part is anti-symmetric.
Yes, yes.
And so it always corresponds.
Yes, yes, yeah. That's why the Hamiltonian interpretation of this oscillation. But usually you have a sum of them. So you don't have, in this matching penny, you just have this anti-symmetric part and you just have the oscillation. But in a general game, you can have both of them. And so it's not, you don't know exactly what you get. Yeah.
Is it true that all games can be decomposed this way?
Yeah, because you can write any matrix, you can decompose any matrix, like the symmetric and asymmetric. And if it's potential, then you don't have the second part, but in general, you have both parts. Yeah.
Right.
And if it's completely Hamiltonian, then you only have asymmetric part, like the matching pennies. So then this energy preserve and the cycles that you can prove that exist. Yeah.
I see. Interesting view. Yeah, thank you.
Yeah, you're welcome.
So there's one question in the chat that says, if the problem is non-convex, are local minima an issue?
Are they an issue in the sense of, yeah, so if it's if the game is non-convex, you can also look at for local Nash equilibrium and try to have algorithms that converge to local Nash. So I guess we will have the same issues as local minima in non-convex problem. I haven't looked at them yet, though it's something that I also really want to look at. I think maybe Lillian, you looked at some of these issues in the non-convex games. But yeah, it is an issue, because you want to go to a local Nash, and even if you think of the potential game, then you will have at least the same issues as you would have in an optimization problem for non-convex optimization.
Yeah, so I have one question if no one else does. Okay, on the slide where you're adding the regularization, you're basically doing that to make the game strongly monotone.
Exactly, yeah, exactly.
And then is essentially that epsilon t, are you decaying it away so that you actually converge?
It's decaying. And the only hard part is how to control the rate of decay. So this is called a single time scale regularized Tikhonov sequence. And there's a lot of analysis. So usually you kind of add this regularization, solve the strictly monotone, strongly monotone VI, and then reduce epsilon t. But because we have only banded learning problem, we need a single time scale algorithm that epsilon t decays at the same time as we are running the iterates of the algorithm. And so I would say the only challenge was in choosing this epsilon t with respect to the step sizes to make sure you go to the Nash while this is decaying at suitable rate.
Yeah, I was trying to interpret this like epsilon t minus 1 minus epsilon t. I don't quite understand what that might be. I guess it just shows up in the analysis.
It just shows up in the analysis.
Okay, interesting.
Yeah, that's a good question. Yeah.
Is there any other questions from folks? Otherwise, I think we'll wrap up since we're 1 minute before 11:30. So thanks again for the great talk. This was a perfect
Thank
fit
you.
for the series.
I'm glad, and thank you all for being here. It's nice to meet you here, and please feel free to get in touch if you have some questions or want to discuss something. And thanks, Lillian, for organizing, and Emily as well. Bye.
Bye.